In this power electronics session, we are going to see about the third type of switched mode regulator, that is buck boost converter. So this type of converter can work either as a buck converter or boost converter. Okay, so the output voltage of the buck boost converter will be either higher or lower than the input voltage. That's why it is called as buck boost converter. So here the output polarity will be opposite to this input voltage. Okay, so V0. Okay, this, see here the polarity of this output voltage will be opposite to this input voltage. So that's why it is also called as an inverting regulator. Okay, now we can see the operation. So as in the case of buck and boost converter, here also there are two modes of operation. So first mode, when the switch is on. Okay, when the switch is on, what will happen? So there will be current through this transistor. Okay, here also we are using the BJT. Okay, any type of transistor you can use, MOSFET, IGBT you can use. So by giving the signal, we can switch on this transistor, and the current will flow through this inductor, and this inductor will start charging. Okay, so it will charge the current from I1 to I2. So the current through this inductor will be increasing from I1 to I2. The voltage, okay, the voltage across this inductor will be VL. VL is equal to VS. Okay, that is the voltage will be appeared across this inductor. It will be the inductor will charge this input voltage. Okay, so VL is equal to VS. So the no current flow in the output side. So it is an isolated area. In the second mode, the switch is off. Okay, when the switch is off, now what will happen? This inductor will discharge its energy now. Okay, it will discharge its energy through this capacitor and through this load. Okay, this diode will be forward biased now and will come to the condition state. So the inductor is discharging in this path. So the inductor is discharging in this path. Okay, so the current through this inductor will be decreasing from I2 to I1. Okay, since it is discharging, the current will decrease from I2 to I1. What will be the voltage across this inductor? Okay, that is VL is equal to minus V. So it has changed its polarity. Okay, so the output is VL is equal to minus V0 since it is discharging. Okay, so VL is equal to minus V0. Now we can see the voltage and current waveforms. So when the switch is on, the voltage across this inductor is Vs. Okay, that is first mode. VL is equal to Vs. In second mode, minus V0. Okay, so when the switch is on, the voltage across this inductor is Vs. When the switch is off, the voltage across the inductor is minus V0. Okay, so when the switch is on, the current increases from I1 to I2. When the switch is off, current decreases from I2 to I1. Okay, so this is the time to turn on period, that is when the switch is on. Okay, this is the period when the switch is off. Okay, so this is the voltage and current waveform. Now we can see the average output voltage and average source current. So we know during the turn on time, the inductor current rises from I1 to I2. Okay, voltage across the inductor VL is equal to L into di by dt. Okay, the current increases from I1 to I2. So we can write during turn on time, voltage across the inductor is Vs. Okay, we have seen in first mode. So VL, instead of VL, we can write Vs is equal to L into the change in current. Okay, that is I2 minus I1 divided by T. Instead of this T, we can put this T on. Okay, because it is turn on time. So we can write this delta I. So Vs is equal to L into delta I by T. From this you can find the value of T, delta I. So delta I is equal to Vs into T on divided by L. Okay, so this is the value of delta I, where delta I is the peak to peak current of the inductor. Okay, then during the turn off time, the current will fall from I to I1. So we can write this equation. Okay, VL is equal to L into di by dt. Okay, VL is equal to in mode 2, that is when the switch is off, VL is equal to minus V0. Okay, so instead of VL, we have written here minus V0 is equal to, since the current is discharging, minus sign. Okay, minus delta I. So L into delta I divided by, since it is turn off time, we have written T off. Okay, So we can cancel this. We can cancel this minus and minus. Okay. So from this you can find the value of delta I. Okay. You can also find the value of t of. Okay. If you want to find the t of, so t of, if you bring here, it will come to the numerator. This will come to the denominator. Okay. You can also find the delta I value. So delta I is equal to, you can bring this term to the numerator. So V naught into T of divided by, it will come to the denominator. So divided by L. Okay. So delta I is equal to V naught T of divided by L. Here this delta I is the peak to peak ripple current of the inductor. Okay. Now we know the value of delta I. Okay. So this is also delta I and this is also delta I. That is during turn on time. This is during turn off time. We can equate both these delta I's. Okay. So if you equate, what will happen? So we can cancel this L. So Vs T on is equal to V naught T off. From this V naught is equal to, if you bring this term here, so Vs T on divided by T off. So V naught is equal to Vs T on divided by this T off can be written as T minus T on. Okay. Already I told you in the previous video, because T is equal to on time plus off time. From this off time is equal to T minus T on. Okay. That is what is written here. So V naught is equal to Vs. Now we can divide all the terms by T to time. Okay. So V naught is equal to Vs into T on divided by T divided by T by T minus T on by T. Okay. So now we cancel these terms. Okay. This T on by T is equal to alpha and T on by T is equal to alpha. So Vs into alpha divided by 1 minus alpha. Okay. See here. So Vs into alpha divided by 1 minus alpha. This is the output voltage of the buck boost converter. You can verify this output voltage. Okay. If the alpha is less than 0.5, if you apply this value over here, you will get the operation for buck converter. Okay. If you apply the value of alpha greater than 0.5, okay, you will get the operation for boost converter. Okay, you can do it by your own. Okay, in the previous video, in the previous buck and boost converter videos, I have shown you the calculations how to verify the output voltage. Okay, here also you can verify how it works as a buck converter and how it works as boost converter. You can verify, okay, by applying these values. So if there are no losses, input power is equal to output power, that is Vs Is is equal to V naught I naught. So V naught is V alpha Vs divided by 1 minus alpha, okay, into I naught. So we can cancel this Vs. Okay. So Is is equal to alpha by 1 minus alpha into I naught. So this is the value of the source current. What are the advantages? Okay. So its output polarity is reversed. Okay. That is also one advantage. Then its efficiency is high. Then the rate of change of current is limited by the inductor L. Okay. So under transient fault condition, the current should be limited. Okay. So it is done by the inductor. Then the output short circuit protection is also easy to implement in this converter. These are the disadvantages. That is, the input current is discontinuous. Okay, so we saw in the first mode and second mode, if you see, the input current was discontinuous. Okay, so in transistor, high peak current also flows. Okay, because when it works as a boost converter, the high peak current will flow this transistor. So these are the disadvantages of buck boost converter. So these are all about the buck boost converter. Thank you.